you for inviting me to speak during this lunch seminar. And what Aparna asked me to talk about was, okay, we have been having this drought going on, and many growers are short on their water supply, especially if we don't get enough rain this season. It could be you're getting surface water allocations and those are cut, or maybe you're on a well and the water table is dropping, and so your well is not producing as much. So how do you manage water so you can grow, enough crops to stay profitable during this drought? So that's really the focus of this talk, and how to think about water management when your water supply is restricted. So let's get going here. So some of the main strategies to optimize water resources under a limited water supply are: first, you need to assess the seasonal water needs of the crops you plan to grow. Then once you know the water needs, you can determine, okay, how much land can you plant and get it to harvest. And that land that you plant, you want to maximize production and profitability. Now you can make that water go further and grow more crops on more land by just increasing your irrigation efficiency. So we'll talk about how you can do that, as well as trying to improve the water holding capacity of your soil more long-term to try to do this so that you can hold more water and store more water actually in your soil. And then for many regions of California, even during a drought, we get winter rains, and often those rains are very intense. And so we want to infiltrate that water and store it into our soils, and also replenish our aquifers. But those storms often are very intense. And so a lot of that water is lost as runoff. And then finally, in many cases, we have to think long-term about developing and using alternative water supplies. So those are sort of the principal strategies that we can look into. Before I really get too deep into this talk, I want to mention that over the years, the UCCE specialists, advisors, and professors have all contributed what we call the drought tips. And so you can go to the UCCE catalog online, and these are free, and they're about 8 to 10 pages in length, all different types of tips about how you can make your water go further in your production. And this is an example of 2 that I authored in the past, but they have this type of format. So they're PDF documents that you can download and print out. And we have this water and drought online seminar series. They're all recorded. They're 30-minute presentations, and there's about 40 of them. So you can take a look at those. Those are hosted at the UCCE California Institute for Water Resources. And some of the people that gave these talks have since retired. So this is a good archiving of knowledge through the UCCE system. So the first step really in planning for drought is to estimate the volume of irrigation water you need to produce the crops you want to grow. And so that is could be divided into these 3 steps. And first is to estimate the water needs of your crop, the pre-season and in-season needs. And so this includes pre-irrigation, crop establishment, satisfying the crop's evapotranspiration demand, and water you need for salinity management, leaching. You also want to estimate contributions from what we call non-irrigation sources. So it could be rainfall. If you're close to the coast, you might get some fog that contributes moisture to your crop, perched water table, or soil moisture that would be stored in the soil. And then you subtract the two, and that is the volume of irrigation water that you need to produce your crop. So I'll just give you a quick example for a broccoli crop, and I'll use this example, throughout the talk. So pre-season, we need about 2 inches of water just for pre-irrigation, so we can prepare the beds correctly. So you have to have some soil moisture there. And then after we transplant, maybe we apply 3 inches of water for that. And then in season, to satisfy the demand of the crop for evapotranspiration, we might have to put on about 20.5 inches. And so we sum that out, and it's a little over 2 feet of water that would need to grow this broccoli crop. So one way of referring to this, I refer to inches or depth of water. Some people would say about 2 acre-feet per acre of water would be needed. Now we could look at the non-irrigation sources. So we know there would be some soil moisture there before we plant the crop that we can take advantage of, and we might calculate that 1 inch available. And maybe early in the season we get a little rainfall, so we get at least 1 inch of that, and there's some fog near the coast, so we get about 1/10 of an inch. So we sum all that up, and that's 2.1 inches. And then we subtract those, and we say, okay, our seasonal water requirement to grow a broccoli crop is approximately 23.5 inches, or about 2 feet, or 2 acre-feet per acre. And if you have any questions, let me know. I guess there's a chat in there, and I can't really see the chat while I'm presenting, but Aparna, you can, stop me if people are getting really confused. Now, I'm not going to do a lot of calculations. These are just simple calculations for planning purposes. Okay, so this is approximately how much water you're going to need to grow your broccoli crop. So you go through this type of budget, but then the next question is, okay, how many acres can you plant and grow with the available water? Now, it's always better to give the crop the water it needs rather than short supply it. In other words, plant less acres if you have to, but don't give half the water to your broccoli crop. You're never going to get good yields. So you really want to optimize the water to grow the best crop possible. So if we had a water allocation, say, of 200 acre-feet, so that's all you're going to get for the season, the question is, okay, how many acres could you plant? And once you know the water needs of your crop, that's a pretty simple calculation. You take 200 acre-feet, divide it by the depth of water that you're going to need to apply over the season for that broccoli crop. And we just convert inches to feet, and you calculate 102 acres you could plant if you had a 200 acre-foot allocation. That's a little more complicated to do this calculation if you're on a well. One reason is, you can't get all the water, when you want with a well, because you're dependent on the flow rate. So we're going to do the same calculation where we have a well that produces 300 gallons per minute at 40 psi. And I want to just mention that every well has a performance curve. And so if you want the water at a higher pressure, you're going to be able to produce less water. So just keep that in mind. And so one One thing is if you're using, say, drip irrigation, we can go to a lower pressure and actually your well can produce more water per unit time than at a higher pressure. But we're saying 40 psi, so it can produce about 300 gallons a minute. And if you haven't done a pump test, I would urge you to do that, because that can give you this sort of performance curve that you can use to figure out, okay, how much water can my pump produce when I'm using sprinklers versus drip. So the questions to ask are, okay, during the, say, the hottest time of the year, what's going to be the peak water use of my crop? And also, what is the application uniformity of my irrigation system? And then how many hours can I operate my pump per week? Maybe you're sharing a well, and so you don't have the full use of it, or there's one day a week your staff are not working. So let's continue that estimate of how many acres could I irrigate at the peak demand, the time of the year when you're at peak demand for your crop. So your flow rate's 300 gallons per minute, and we might determine that at the hottest time of the year, your broccoli crop is going to use about a 1/4 inch per day. You're irrigating it with sprinklers, and so your application uniformity, let's say, is 75%. 100 is perfect, but you're getting, which is typical for sprinklers, about 75% uniformity. And you don't want to operate your well more than 12 hours per day and 6 days per week, because your staff take a day off. So first, we calculate the water requirement, and that's a 1/4 inch per day. Now the plants don't take a day off, so it's 7 days a week they're growing. So if it was like the hottest time of year, they're using a 1/4 inch a day times 7 days per week. And then we adjust for the uniformity of the irrigation system. And we need 2.3 inches of water per week per acre. Now we want to convert that depth to gallons. And we do that by multiplying by this factor 27,154. That's how many gallons are in an acre inch. If you spread water over an acre, 1 inch deep, you have 27,154 gallons. So we can convert that to the gallons you need per week per acre, which is about 63,000 gallons for each acre of broccoli you're growing. Now we go and look at the pump capacity and convert that into gallons. And so we multiply the 300 gallons per minute times 60 minutes per hour, and we're operating it 12 hours a day, 6 days a week. And that's about 1.3 million gallons of water we produce per week. And by dividing those two numbers, we can estimate that we could irrigate 20.5 acres with that well. So that's probably the most math I'll be doing in this talk, but this is sort of how you have to think about it when you're planning with a limited water supply. So what do you do if the water supply is not enough to grow crops in all your acres? And as I mentioned before, you don't want to short the crop because it's going to suffer. You won't get good yield. You want to cut down the acres that you're going to cultivate. Well, one thing you want to do is farm the best fields possible and grow the most profitable crops. So you look for the fields that have the most suitable soil types, maybe uniform and a shallow slope. They should be well-drained fields, the least weed pressure, highest fertility. So this is where your records are really, really important to know this. low incidence of soil-borne diseases, and you want to avoid fields, where you have compaction zones, excessive slope, or maybe there's high salinity problems there. Then if you might be able to be a little more profitable by selecting varieties that are higher yielding or shorter season varieties, so they don't use as much water. And you really want to optimize your pest management and fertility program. So again, for the land you are have under cultivation, you're getting the best yields and quality possible. Now, another approach is to be more efficient with your irrigation so that you can grow, use less water. And so for the amount of water you have, you can spread it over more acres. So one way we can do this is improve the application uniformity of your irrigation system. And so here is an assessment of uniformity of a sprinkler system. We put these buckets out, and what we want to see is similar amounts of water in those buckets. That means the water is going on very uniformly, but sometimes, say in the middle there, between those sprinkler lines, we have less water. As a result, you have to irrigate the whole field longer. And so just to keep up with the water needs of one zone in the field, you're applying more water to the whole field, more than the crop actually needs. So it would be better to use that extra water in another field, right? With sprinklers, if 100% is a perfect uniformity, we usually can get 75 to 80% uniformity. With drip, we can usually get 85 to 90% uniformity. So it has a potential for higher, what we call distribution uniformity, or you could call it application uniformity. So drip has potential for high application uniformity, and it's very efficient for salinity management. You can inject fertilizer through the drip system. Because you're not wetting the leaves, often you get better yield and quality. So this is another calculation, but a very simple one, just to illustrate how you can make that water go further by increasing your irrigation efficiency through improved application uniformity. So if you looked up for the broccoli, in that table I showed earlier, it has a typical evapotranspiration demand over the season of just 13 inches. But if you're using sprinklers and your distribution uniformity or application uniformity is 70%, or in a decimal form, 0.7. And then you need a little extra water for what we call a leaching requirement. So salts don't build up, and say that's 10%. Then if we do this math here, you find out the water requirement for this broccoli crop is 20.6 inches. So that's where that 20.6 inches comes from that I was showing earlier in that assessment of the water needs for the season. Now, if we switch to a drip system that has a high distribution uniformity or application uniformity of 90%, then just by changing this one number from 0.7 to 0.9, we can get away with 16 inches of water. So essentially saving about 4.5 inches of water. So that 4.5 inches can go somewhere else in terms of your production. So a 90% uniformity with drip is optimal, but the reality is sometimes growers don't manage their drip systems to take advantage of the potential uniformity. So it's very important to make sure whatever irrigation system you're using, you're optimizing its application uniformity. So fixing leaks, often drip is operated at very low pressure, but too low of pressure, and then the uniformity goes bad or goes down. So you want to make sure you stay in that 8 to 10 psi pressure. If you're injecting fertilizer, especially organic fertilizers, you want to make sure you're doing that before filters so you don't plug up emitters, and you want to make sure the design is optimized to have very uniform pressure everywhere in the field. So pressure management is very critical to drip because you're operating the drip system at a pretty low pressure, where sprinklers would be at 45, 50, 60 psi. We're talking about drip systems that work optimally at 8 to 12 psi. So you want to be able to check the pressure all over your drip system, and we can put pressure gauges, but I like using these Schrader valves and then checking the pressure with the same pressure gauge. It's sort of like comparing apples and apples, because you'll find these pressure gauges that you buy from the store, they vary brand new 2 or 3 psi from each of them. So if you're talking about 2 or 3 psi of variation, between gauges, and we're trying to keep the pressure at 8 or 10 psi, you already introduce some variability there. Another tool we can use in drip systems are pressure regulators, or these are called pressure reducing valves. And what this will do is when you open another block, you're irrigating, it will automatically control a valve here to maintain the downstream pressure for whatever you set it at. And so you adjust what pressure you want here, and say you want it at 8 psi. If the upstream, the water pressure shoots up, this is going to close down just to maintain it at 8 psi, and vice versa. If you open up another block, you want to irrigate, the pressure drops here, then this valve will open and maintain the pressure. So it's really a critical part of a drip system, is to have these pressure regulators. Then with sprinklers, we also want to optimize uniformity. And one issue that we see a lot is the nozzle sizes either get worn or they're mixed of different sizes. And so the nozzle size or the orifice size has a lot to do with how much water comes out of each of those sprinkler heads. Again, pressure management is important for sprinklers. They don't perform very well often at too low of a pressure, and going to really high pressure is not necessarily a good idea either. So you want to watch the pressure management, the lateral spacing. If you put your sprinkler lines too far apart, you lose uniformity. And also, obviously, operating them in wind, once you get beyond 5 miles an hour, you lose your uniformity. Now, there are sprinkler heads besides these brass impact sprinklers, such as these more modern plastic rotator sprinkler heads that can provide higher uniformity. And there's lots of different models now that you might want to check out. So the other aspect to increasing irrigation efficiency is improving your irrigation scheduling to better match your applications with what the crop needs. And there's different approaches. We can use weather-based, plant-based, or soil-based. And ideally, you'd use a combination of these different methods. So with soil moisture monitoring, we can monitor the volumetric moisture using sensors like this one. Or we might look at the soil moisture tension, how hard is it for the plant to pull water? And so we use this sensor that has a vacuum gauge. And when the vacuum is higher, it means the soil is drier. And it's a good simulation of what the plant is experiencing. I also think the problem with soil moisture sensors is they're pretty much in 1 or 2 spots in the field. So if you use a soil moisture probe, and just feel the soil and probe around, especially with drip systems. Water doesn't go evenly from the drip line through, through the cross section of your bed. So probing around gives you a good sense of where the water is and how moist the soil is. And there's tools to utilize, checking the water status of your crop. For trees, stem water potential is a very good tool to use. It's labor intensive. For some of the agronomic crops, just looking at the canopy temperature can also tell you if the crop is under water stress. Neither of these tools are used much in vegetables, but for agronomic crops and tree crops in vineyards, they can be very useful. Weather-based irrigation scheduling is utilizing this network of SIMA stations we have throughout the state to estimate the crop water needs. And that could be an extremely useful tool for irrigation scheduling. You get a reference ET, and you can get this online from the SIMA's website, and you multiply it by a crop coefficient to estimate the water needs of your crop. And so this is showing that the crop coefficient starts out low and then it goes up to a maximum and drops off maybe late season if you have senescence of your leaves. And we found in our research that the crop coefficient is very much related to the canopy cover or the foliage cover. And so this can be evaluated. You don't have to use a camera like this. There's tools like that you can use with your iPhone. One is called Canopeo, and that gives you a sense of what the canopy cover is, and then you can use that to adjust your crop coefficient. We also, as Aparna mentioned, developed this online tool, Crop Manage, that can help you with irrigation scheduling. We've modeled the canopy cover development and the crop coefficient, so it will automatically pull in that SIMAS reference ET value and do all the calculations to tell you how long to irrigate. How frequent to irrigate is going to depend on the weather, the ET demand, and the water holding capacity of your soil, the rooting depth or the volume of soil that the crop is exploring, and the threshold of when you are depleting the soil moisture to a point where you're stressing the crop. And I just showing you in this table from a sandy loam to a silty clay loam, that if we take it down to 30 centibars of tension or 80 centibars of tension, this is the amount of water you could deplete. So with this clay soil, you can deplete more water than with the sandy soil. And that's probably well known to many of you, but the amount that you can deplete is not a lot once you go down to 30 centibars or 80 centibars for every foot of depth. Here it's 0.65 inches you can deplete and use for your crop before it gets stressed. Now, once you know how much water your crop's using for each irrigation, then you have to figure it out in hours, how long to irrigate. And so you must know the application rate of your irrigation system to do that. This is a table that shows you for impact sprinklers for different nozzle sizes and pressure, how many inches per hour that system puts out. And you can see it can vary a lot. Just a 7/64 nozzle, which is quite common, it could be almost a 1/4 inch an hour up to 1/3 of an inch an hour. Another way we can spread that water on more land and use it more efficiently is optimizing irrigations for establishing the crop. And so this is an area where I often see growers over applying water. Is when they first transplant or they just seed the crop, they put a lot of water on, and probably more than they need to. So what you want to do is evaluate your starting soil moisture content before you start the first irrigation. And if the soil is very moist, you don't need to irrigate, for 10 hours. So often, that first irrigation with a few hours with sprinklers, that's enough to wet that seed. And thereafter, you don't want to apply much more than twice the evapotranspiration, the reference evapotranspiration value for those days. So if it was a 1/4 inch a day of ET, you don't want to do much more than a 1/2 inch per day. And you want to make sure that your sprinklers or whatever irrigation system you're using has a high application uniformity. And if you're using sprinklers, operate them, irrigate under low wind conditions. Again, you can do a very short sprinkler irrigation, maybe just 1 hour each day, but make sure that 1 hour is the best hour of the day in terms of operating the sprinklers. Then if you can maximize your soil's water holding capacity, also the rooting depth of your crop, you could take advantage of moisture that would be stored in your soil that's infiltrated during the winter period. And so growing cover crops, adding organic amendments, improve the porosity of the soil and its ability to hold more water. Also, if you have any impeding layers of the soil, the roots can't get down to that moisture. And so it is important to break up those layers periodically. So one of the water sources we do have are our winter rains, and sometimes we get the rain so intensely they just run off the fields and actually cause flooding downstream. The more of that water we can get into our soil, you have moisture for storage for your next crop in the springtime, but also you are infiltrating water back down into the aquifer. And unfortunately, where I'm located, historically, growers don't have a lot of winter cover crops in the ground. And so the soil sort of seals up like this and it runs off when it's when it's raining. So winter cover crops, of course, can help in terms of reducing stormwater runoff, as well as prevent nitrate leaching by taking up nitrogen that might be in the soil. And they build organic matter and improve the macropore structure of the soil, so you have more water holding capacity. But the reality is a lot of the vegetable growers want to get into their fields early in the season. So they don't want cover crops that are going to be difficult to incorporate. So we have in the past looked at these low residue short-term cover crops. So we have peaked beds and we just plant in the furrows. And then for conventional farmed areas, we can put an herbicide on and kill that cover crop after 60 days. And we have this organic material on the surface, which can help reduce runoff issues. You could also do this organically. You probably wouldn't grow, say, this is a barley or triticale crop, but we found with some of the mustards, you could kill those mechanically and use that residue on the surface. And that residue breaks down over time. But what we noticed was it really helps infiltrate moisture into the ground during these rain events. So this was a trial we did, and you see where we have bare areas over the winter, 47% of the rain ran off the field, which was about 120,000 gallons an acre. Where we grew triticale, only 9.2% ran off the field. The rest infiltrated, and so it was only 30,000. So it was about 90,000 gallons per acre we were infiltrating just by having that triticale. And then where we had rye, it did even better. So we're infiltrating about 110,000 gallons per acre over the season. So that really helps store moisture. Also, we had less soil erosion. And so you can see, where it was bare, we're losing about 1,200 pounds of topsoil per acre through this storm runoff versus only 2 pounds per acre where we had the rye. Lastly, I just want to mention that you have to think long-term because we're in an area where droughts are reoccurring for developing and using alternative water sources. So on the coast, we've developed this recycled water supply. So we're using the sewage water from the urban areas and it's going from secondary to tertiary treatment and distributed through we call it the purple pipe to growers. And on the Central Coast, this irrigates about 17,000 acres now. So a lot of growers are utilizing it, and it takes a little while to understand, its limitations because it does have higher salinity. It has higher nitrogen content than maybe their well water. And then other growers are capturing their tailwater during the irrigation season and putting it into these retention ponds. And the idea is then they can reuse that water into their for germinating up their crop or for pre-irrigation. They don't use it for leafy greens during the season because they're concerned with food safety. And they also do a treatment of this water with chlorine to make sure they don't have any pathogens that would cause harm to humans. So I'm going to wrap this up by just summarizing, our main water conservation tips are, again, assess the crop water needs, maximize the production and profitability of what you do grow. Do whatever you can to increase your irrigation efficiency so you can spread that water over more land. Improve, the water holding capacity of your soil. Make sure you're doing whatever you can to infiltrate winter rains, and look long-term for developing and using alternative water supplies.